Calc BC, we're still in lesson 4.3, a longer lesson. Let's go to example 4. Here we have a polynomial. We'd like to use the second derivative test. We changed the directions to find local extrema. The second derivative test really will require us to proceed just as we always have with even finding critical numbers. We'll take our first derivative. We'll get 4x cubed minus 12x squared. And we're going to set this equal to 0. Well, before we even begin, we are going to need a second derivative. We might as well do that real quickly. That wouldn't take too long, would it? A second derivative would get you a 12x squared minus 24x. That being said, however, we are focusing on our critical numbers. And it's only going to take us a moment to find that. So I'm going to factor out a 4x squared from both of these. That's going to leave me with an x minus 3. So what are the critical numbers? Well, the critical numbers, very quickly you can see, would be x equals 0 if you had 4x squared equals 0. And also x equals 3. Now, from here, I'm going to go ahead and substitute these values into the second derivative. This is why we call it the second derivative test. Look, if I did y double prime of 0, we'd have 12 times 0 squared minus 24 times 0. This is going to be a second derivative value of 0. By the way, that's kind of a bummer. What we're seeing right here is our third possibility. When our second derivative happens to be 0, we get no concavity. We can't say we have concave up or concave down for our curve. This right here, we're going to have no conclusion. And sadly, the first derivative test is going to have to get used at the end of this. We are going to have to keep going with this, so we're going to need the first derivative test. We'll get to that in just a moment. But over here with x equals 3, y double prime of 3, we'd have 12 times 3 squared minus 24 times 3. And 9 times 12, well, that's 108. And minus 72. Rest assured, you're not even really concerned with what the exact value of the second derivative is. You just know it's positive. So what do we know now? We can say that when we have a positive second derivative, our curve is concave up. We also know that at x equals 3, our first derivative is 0, meaning we have a horizontal tangent line. The second derivative test is going to show us very clearly that we have a local minimum. Now, if we were to find out what y of 3 was, we can do that right up here. That's going to be 3 to the 4th minus 4 times 3 to the 3rd. And this, of course, is also where we can get some help with the calculator if the numbers are, in fact, getting bigger. We could say real quickly, 3 to the 4th, by the way, is just 81. So it's not like that's horrifically bad. You know, just crunching some numbers here, you can see we get negative 27. So what I'm going to say is there's a local min of negative 27 at x equals 3 because f prime of 3 equals 0 and f double prime of 3, or y double prime of 3 if you'd like, is greater than 0. That's your second derivative test. We didn't do a number line whatsoever. We were just able to look at the concavity. We had a concave up curve with a horizontal tangent line. So that can be very helpful. However, as we're looking over here at x equals 0, I just want to test to the right and to the left of 0. We do need some help here with the first derivative test. The second derivative test, sadly, let us down. And what was f prime? Well, f prime, or y prime, if you would, was 4x squared times x minus 3. When you plug in a 1, x squared is always positive. 1 minus 3 is negative 2. So this is something negative. So f of x is decreasing here. When you plug in a negative 1, you can do that just as well. Negative 1 minus 3 is going to be a negative 4, and this is still positive, so it's still negative. In other words, we don't get a change in the sign. We can see that there's not going to be a relative max or a min at x equals 0. So that is also very helpful as well. We can say because f prime doesn't change signs at x equals 0. There is no extrema there. So be aware that's going to happen a lot also, where you won't have a max or a min at a certain x value. Just because you have a critical number, that's no guarantee that that's going to be occurring. Well, let's real quickly take a look at our last problem, number 5. And, at first glance, this is going to look just like a test question. It's going to look like a problem that we've had before. It says, given that f is a continuous function, use the table below to estimate f of 3.2. And here is f of 3. Just want to tell you all this other stuff is superfluous. It really doesn't come into play. We can say that we have the point, f of 3, that's going to be 0.141, or we've got the point 3 comma 0.141. That's where we're beginning. But we'd like to know what's happening at f of 3.2. And if this seems to ring a bell, if you're going to be thinking, my gosh, this looks so amazingly close to what we did in chapter 3, it is. We're going to use a differential. dy, well, we're going to make this our x naught. Our x naught is 3. If we're going from x equals 3 to x equals 3.2, your delta x is 0.2, isn't it? So we could say, well, dy is going to be f prime of 3 times a delta x of 0.2, and f prime is negative 0.990. And it won't take you too long to get this thing going here. You could say, okay, if we just get this thing turned on real quickly, and it looks like my calculator is having some issues. There we go, negative 0.990 times a 0.2. You could see that's negative 0.198. And that's your dy. But please understand this is your change. This is a review problem up to this point. We could say, what y value are we starting with? Well, we're starting with 0.141. And then you could think, well, what kind of change just took place? A negative 0.198. So my goodness, we could real quickly just take that negative 0.198 and add 0.141 to it and get negative 0.057. So someone could say, hey, what is f of 3.2? What do you think it's approximately equal to? Well, we could say it, I would say it's pretty close right here to negative 0.057. That's what we'd expect. But there's another part to the problem. You just made an estimate. Is it too big or is it too small? Well, there's one part of the table that you probably haven't really made use of so far. And that's right here. The fact that f double prime is negative at x equals 3. So tell you what, we're going to real quickly think about that. When f double prime is negative, your curve is concave down. Concave down like a frown. So f is concave down at x equals 3. It's like a frown. And guys, I hope you can see anywhere where you build a tangent line. That tangent line will touch your concave down like a frown at one point. Everywhere else, the line is above, it's higher. It's above that. So what you do is you could say because f double prime of 3 is negative, our estimate is an overestimate. Here's why. A differential is working with a tangent line. Your tangent line is above your curve here. And if it's above, that means your y values are too big. Your approximation is going to be an overestimate. By way of comparison, if you would have had a concave up kind of a scenario, then your tangent line would be under, and that would be an underestimate. So hope this is making sense. Long lesson here, but a very important one.